So today our presenter is Professor Chris Scott from the University of Reading. Chris completed his PhD in 1993 at the University of Southampton. He then moved to the Rutherford Appleton laboratory, initially working with IceCap before becoming a project scientist for the heliospheric images on stereo spacecraft. In 2010, Chris moved to the University of Reading, where he now works as a professor in space and atmospheric physics. Chris's primary research interests include improving space weather forecasting, the ionospheric enhancements in response to lightning, solar wind influence on lightning rates, and long-term changes in the ionosphere. Chris is also an enthusiastic citizen science advocate and PI for Solar Storm Watch. Today, Chris will be presenting 100 years of Appleton's ionosphere, and so I'll let Chris take it away now.
Thanks, Gemma. Well, thank you for coming, everybody. So yes, 2025 represents the 100 years since the publishing of a paper by Edward Appleton proving the existence of a reflecting layer in the ionosphere, in the atmosphere, called the ionosphere, or later to become known as the ionosphere. And so I've been sort of delving back through the records to see what we had and what we could, what I could show you about what those experiments were. But if we cast our minds back to the beginning of the 20th century, people were using radio. It was quite often used for Morse and the like, for communications and ship to shore, that kind of thing. But there was a lot of pioneering work going on, particularly by the Marconi company, to see how far you could transmit radio waves. And on the 12th of December 1901, Marconi is credited with sending the first transatlantic radio signal, and it was transmitted from a place called Poldhu in Cornwall. I don't know if anyone's been there. I have. It's a really well, remote part of the UK, really. And there's some photographs here of the Poldhu station. Initially, there was this circular array of antennas, but they were blown down in a storm just around the time of the initial experiments. And so latterly, you can see on the top left there, a series of 4 towers were built and an antenna array was rigged between them. Well, this was a spark transmitter, and the picture in the top right there shows you the transmitting building, inside the transmitting building. And the sign basically says, "Very dangerous, strong, well, stay clear." Yeah, so there's very, very powerful. But the actual spark transmitter is over by the window. You can see two balls actually quite close together. So it really is pioneering stuff. So up until that point, people didn't know how far you could transmit a radio wave. And if you look on Google Maps at Poldhu today, you can still see the remains of the hut sort of mouldering away in the field. I don't know if you can see my cursor, but it's just here. And then there's a circular feature in the field, which is the foundations of that initial circular array. Well, in 1901, Marconi positioned himself in Newfoundland to receive a signal, and it's about 3,600 kilometers away. And so this Google Map animation gives you some indication of the scale of that experiment. So Signal Hill was a remote location, and we can zoom back down onto that. There's no evidence of the arrays that I can see in the Google Maps images, and I don't think the car park was there in 1901. But this is where Marconi was waiting to receive the signal. Now, it's a very poor experiment, really, in that it was the Morse code letter S was transmitted from Poldhu and at a known time. So Marconi knew what he was listening for. And so people have theorized that as to whether this actually occurred. But we know that radio waves can travel long distances. And people at the time were trying to work out how you could get a signal received at Newfoundland. Some people thought that there was the conduction of the sea. So if you broadcast your radio wave in all directions there, we're interested in the ray that's traveling towards Newfoundland. Light travels in straight lines. So how did it actually curve around the Earth? Well, some people suggested that perhaps the radio wave was interacting with the ocean in some way. The ocean is salt water, it's conductive. Was there some sort of refraction happening in the oceans? But there were two scientists independently who were thinking about the problem, Kennelly and Heaviside, and they proposed that there was a radio reflective layer in the upper atmosphere that you could bounce radio waves off and thus send signals over the horizon. Now, people have subsequently looked at the experiment, and Jack Ratcliffe wrote quite an interesting paper in the 70s looking back at this experiment and suggested that perhaps while the transmitter was at quite a reasonably low frequency, that there would have been quite strong sidebands at around 3.5 megahertz, and those were much more likely to have been received at Newfoundland, given that the antennas that they were using to receive the signal were broadband themselves. There was no frequency tuning on the receivers. So they knew that there was a reflecting layer, or that there was some means of propagating radio waves around the horizon, over the horizon. But it wasn't until October 25 that Edward Appleton and his student Miles Barnett conducted some experiments that demonstrated that it was a reflecting layer. And Appleton's research was into listening to radio signals, and particularly at night, he noticed that you got a fading of the radio signal. It faded in and out, and people didn't quite understand why the radio wave was doing this. And Appleton was proposing that this was because there were two paths of the radio waves that were traveling different distances, and as a consequence, they were arriving out of phase with each other and causing interference fringes. And so here's an example of some recordings that were taken just after sunset. And he's measuring the electric field with a galvanometer here, and you can see that there are these beat frequencies which Appleton was claiming were caused by two waves traveling in different paths. Well, assuming that there was a reflective layer in the upper atmosphere, excuse me, Appleton referred to these as the ground wave and the sky wave. And he noticed that this effect was most prominent when you had a receiver about 100 kilometers away from the transmitter. So on the 11th of December, 1924, Appleton arranged for BBC Bournemouth to transmit a known frequency, and he set himself up in Oxford to receive that. Now, there's very little left to show of the existence of Radio Bournemouth. There's some photographs in the archive and a fantastic piece of movie footage here. As you'd expect in Bournemouth, it's surrounded by bungalows. I can say these things, I grew up in Bournemouth. But it was quite a modest building, really. You can see it was just a sort of prefabricated hut with the antennas mounted across the top of it. And we even have the Bournemouth calling signature tune there, if anyone wants to reimagine the actual sorts of things that were broadcast. So while BBC Bournemouth doesn't exist anymore, the plans do, and this is what the plans would look like. It was set up on the edge of Bushy Road in Bournemouth, and with the magic of Google Maps, we can see what the place looks like now. You can see that those bungalows in the background are still there, and the site was eventually overbuilt by bungalows itself, and it sits on the edge of the cemetery at Bournemouth. So again, using the magic of Google Maps, we can travel with the skywave from Bournemouth. You might want to hold on to the edge of your seats for this one because it's quite dizzying. But the ground wave will be traveling from Bournemouth all the way across country to Oxford, where Appleton had set himself up in the electrical laboratory to receive the signal. So we're going to look down now on the electrical laboratory. And then if we go back up to get the view of the scale of this experiment compared with Marconi's experiment, you can see that it's much, much smaller, and there's a much higher likelihood of receiving both a wave along the ground here and a wave reflecting off the ionosphere. So Appleton proposed that this was analogous to the Lloyd's mirror experiment, where you could have interference fringes being produced. And he talked about the geometry of the experiment. If you had a path A along the ground, a path A dash that was somehow being reflected from the sky, then the difference in path length, A dashed minus A, would give you a number of wavelengths difference of the two signals, one going by the ground and one going by the sky. But the ingenious thing that Appleton did was that he arranged for the transmitter to be the frequency of the transmitter to be changed by a small amount delta lambda. And if you do that, you can rearrange these equations to have the form there delta lambda over lambda squared multiplied by A dashed minus A. And the number of beat frequencies that you see is equal to that expression. And we know everything apart from A dashed. And so by counting the number of maxima and minima in the received signal, you can work out what that A dashed path was. And Appleton was able to work out that from this, that the height of the ionosphere, or the reflective layer that he had discovered, was at around 100 kilometers. So this became known as the frequency change method. You'd gradually change your frequency, you'd count the number of fringes produced. If you actually look at this paper, Appleton doesn't present any results in it. It's quite astonishing, really, that this was the experiment which was cited in his Nobel Prize. He didn't actually produce the results. He just said he watched the needle of a galvanometer and counted the number of fringes. And from that, he was able to estimate the height of the atmosphere. So it was all really taken on trust initially. Well, why are there layers in the atmosphere? Well, it all comes down to the fact that we have ionizing radiation coming in from the sun, and the intensity of that ionization decreases with height as it gradually gets absorbed by the Earth's atmosphere. The Earth's atmosphere, on the other hand, decreases exponentially as you go up through the atmosphere. And so at the top of the atmosphere, you have a lot of radiation, but not much atmosphere to ionize. And at the bottom of the atmosphere, you have a lot of atmosphere to ionize, but not much radiation. So somewhere in the middle, there's a Goldilocks zone where an ionospheric layer forms. And I have some nice slides, which I should have been stepping through as I said all that. So having discovered that there was this layer at 100 kilometers, which became known as the E, or electrified region, further scrutiny was required to understand how that varied both with time of day and with season. And it was soon discovered that the layers did change very much between day and night. And we have a cartoon here from the Encyclopedia Britannica, because the lower regions of the atmosphere, the ionization, the individual ions only have a lifetime of seconds or subseconds. And so as soon as the sun goes down, those layers disappear. Whereas in the higher ionosphere, in the F region, the atmosphere is sufficiently tenuous that the recombination is much lower, and the chemistry is different. So in Ratcliffe's book, he demonstrates actually what's happening here, with a quite neat little thought experiment, is that you have an electric field in the radio waves, and those set the electrons, the free electrons in the atmosphere, oscillating. And the frequency with which they oscillate can be estimated by imagining a box of plasma, and you move artificially all the electrons up a distance x, and that generates an electric field and a restoring force as a result of that field. And you can substitute in the values for that, and you get a frequency, a radio frequency, which is equivalent to, if you put all the numbers into all those values, about 8.98 times the square root of the electron number density. So it's one of the few equations I can actually remember, is the radio frequency is equated to the electron density by 8.98 times the square root of the electron density. So for the sort of densities of electrons we get in the Earth's upper atmosphere, this equates to about 1 to 20 megahertz, the resonant frequencies, depending on how dense how the density is varying, and that happens to be high frequency radio, so shortwave radio, the sort of frequencies that Marconi and the BBC were using. And this is a little cartoon to try and demonstrate how you get a radio wave refracted by the ionosphere. Well, if you look at the lower panel here, each white dot there is an electron, and you have more electrons at the top than you do at the bottom. So there is this sort of a layer forming, and there's a radio wave moving horizontally through the layer, and the peaks and troughs are represented by the black and the red lines. But every time the radio wave interacts with the electron, it sets the electron oscillating, and the oscillation of that electron re-emits the radio wave, but with the phase advanced by about 90 degrees, well, by 90 degrees. And so you can see that what this does is, if you have a wavefront moving through a plasma with irregular densities, that wavefront gradually gets refracted until it's angling down. And if you are broadcasting from a transmitter to a receiver, then you can estimate the maximum frequency that you can use to skip off the ionosphere by considering the geometry, where the maximum frequency for vertical reflection of the radio wave is considered to be the value f0 here. Well, Appleton had his frequency change method, but around the same time, a bit later in that year, two engineers in the US, Breit and Tuve, that had developed a technique of amplitude change. So they would create small pulses of radio waves and use those and time the reflection of those back to the ground. So they were able to use amplitude change method rather than this frequency change method that Appleton had envisaged. But the scientists, Appleton and his colleague, realized that this was a useful technique to use, because if you could change the frequencies, you could gradually probe through higher and higher layers of the ionosphere and actually build up a profile of what the plasma densities were as a function of height. So in this cartoon here, you broadcast a radio frequency of 1 megahertz, and it is returned from the height where the plasma frequency is 1 megahertz. Increase your radio frequency to 2 megahertz, and it returns from a slightly higher altitude. Go up to 3, higher still, and the peak frequency of the layer here is 4 megahertz. So that's the highest frequency you'll be able to reflect off the layer. And if you use radio frequencies any higher than that, they will go through the peak frequency and will be lost to space. So by looking for the peak frequency, the so-called critical frequencies that you could reflect from each layer, then you could work out what the peak density was. But lower down in the ionosphere, where the atmosphere, the neutral atmosphere, is much denser, once you set an electron oscillating through absorbing the radio wave, those electrons have a much higher chance of colliding with the neutral atmosphere, and that disturbs the oscillation, and effectively the radio wave is absorbed by the atmosphere and dissipated as heat. But there's two ways you can absorb a radio signal. So it's called non-deviative absorption lower down, where the radio wave isn't necessarily being refracted, but it's having its radio wave energy absorbed by the neutral atmosphere. But you can also get what's known as deviative absorption, and that's where your radio wave is approaching the critical frequency of the layer, and it's being absorbed and re-emitted and absorbed and re-emitted, and that slows the radio wave down compared with the radio wave traveling in free space. And the longer it hangs around in that region, the more chance are that there is a collision and that the radio wave energy will be dissipated as heat. Well, having set themselves up to probe the ionosphere using this amplitude change method, Appleton and his colleagues set up a sequence of measurements at the Radio Research Station in Ditton Park in Slough. And this is a picture of Ditton Park in the 1930s. Very rarely I give a talk which doesn't show pictures of sheds at a field, but it's a very archetypal British way of doing experiments, I think. And each one of these sheds has got different antennae on it. There's some marvelous pictures in the UK Solar System Data Centre that's curated by Matthew Wild. in which there are sheds that are hoisted into the air, sheds that are on rails that can be rotated. But the shed that we're interested in for the purposes of this talk is the shed here at the back, hut number 14. And you can see, has a mast next to it, and a big radio wave, a big radio antenna can be mounted from that. And from this, some of the very first sequences of ionospheric sounding began. And these are the photographic records of that very first run that started a sequence which continues today. So on these plots, frequency increases from right to left. The big thick line at the bottom here is the ground. So you were getting a direct measurement from transmitter to receiver at the ground. And then returns from the ionosphere were delayed by their travel time. And so you can see on the graph these layers at higher altitudes. And as you increase the frequency, it goes through this lower E region on the right, and then starts to be reflected from a higher layer, which was the F region. You can see that there's some attempt here for height markers. They would have some local oscillator that would resonate at a set timing, and so you could therefore work out the time it had taken for your radio wave to be returned. And assuming that this radio wave had traveled at the speed of light, you could estimate a height. But of course, we know it's not traveling in free space, and so there had to be a correction for the underlying ionization. Well, this is the sort of apparatus that they were using. And it's been quite fascinating to try and work out how the records were taken. So let's start on the right here. You can see there's at the top right here, there's a cathode ray tube, and that would be showing the two dots from the ground return and from the ionospheric return. And then sitting on the stool in front of it here is a camera that would be clamped to the front of that cathode ray tube. And as a consequence, if you fed photographic paper with a clockwork mechanism past a slit in that tube, as you changed the frequency, you would create this analog graph, which had become known as an ionogram. I'll go into the whole the mechanisms by which this was done in a second. Well, the sequence that Appleton started back in the 1930s continues today at the Rutherford Appleton Laboratory in Oxfordshire. And this is an example of a modern digital ionospheric sounding. So you can see now that the frequencies go from left to right, that the radio frequency here in megahertz go up from sort of 1 to 15. And the virtual height now is actually marked in kilometers. There are two colors here. There's red and green. That's because the ionosphere is birefringent. So depending on whether your radio wave has a clockwise or an anti-clockwise polarization, it will interact with the Earth's magnetic field in different ways and have different pathways. But the layer that's most commonly examined is this so-called ordinary ray here in red. And so you can see on this ionogram, there's a very strong F region. And as you approach the critical frequency of the layer and the radio wave is being absorbed and re-emitted and absorbed and re-emitted, it takes much, much longer to return to the ground. And so you have these asymptotes that gradually go off to infinity. And at that point, the radio wave is at a frequency where it is just going through into space. So the highest frequency of each of these waves tells you the peak electron density of each of the features. Recording the whole ionogram, although the ionograms from Slough have been preserved, they're all quite different. They're quite changeable. They can be quite noisy. And so it was set out fairly early on to actually identify certain features that could be tabulated. And so there was an army of women, mostly, almost entirely, I would think, who were tasked with identifying the peak frequencies of each layer. So here is the F0, F2, the peak frequency of the F2 layer. There's an intermediate layer, the F1 layer here, and so that's measuring the peak frequency of the F1 layer. and likewise the peak frequency of the FOE layer. And then the virtual heights of each of these layers, considered to be the lowest altitude in that layer, so the furthest from either of these locations where there was a lot of delay because of the deviative absorption going on. Those were considered the virtual heights of the layers. And these quantities have been tabulated. But there's a lot more information you can get out of the actual ionogram. The prominence of the F1 layer, for example, tells you something about the chemistry of the ionization. And here's the long-term sequences of Slough. These are now monthly means of the noon value. And for the top of this plot here, we can see that there is the sunspot number varying with the well-known 11-year cycle. And you can see that 11-year cycle in the Slough sequence. And you can also see the annual variation superimposed on that. So here, F2 is blue, F1 is green, and the E region is the red layer here. And for comparison, we also have the sequence from Stanley in the Falkland Islands, which is another extremely long sequence that was started in 1945, but unfortunately maintenance issues means that it hasn't been continuing of late. But these data are still in demand. People are still using them to determine radio communications conditions and response to any space weather events. Well, I'm a keen advocate of the Slough data sequence. I've done lots of science with it over my career, and it contains all kinds of information. So, for example, we did some research with a superposed epoch analyses here at the top to show that if you took the time of lightning as measured by the UK Met Office's lightning detection network, and you aligned all those lightning events at time 0, and then looked at the sporadic E layer, which is a layer of ionization generated by the ablation of metal from meteors coming into the atmosphere, you could see that the strength of that layer was enhanced after lightning. And this is likely due to the fact that lightning is one part of what's known as the global electric circuit. So lightning to the ground, and also there are upwards discharges of charge to the upper atmosphere, forms the sort of battery of the circuit, if you like. And then everywhere else where there isn't a thunderstorm, that charge from the ionosphere leaks back down to the ground in what's known as the fair weather electric field. And so it's not surprising, therefore, that the ionosphere sits at a charge at about 250,000 volts compared with the ground. And so there must be some interaction. And the reason it shows up in the sporadic E layer is that these metal ions hang around for hours. And so after they've been ionized. And so they show up very clearly in the hourly routine measurements from Slough. Another superposed epoch study was looking to see what the effects of explosions were. So this was really inspired by the lightning research. Was it an electrical effect? Was it a shock wave being launched that was causing ionization to be intensified through some sort of wave action? So if you could use explosions alone, does that show the same thing? You don't see any effect with the sporadic E layer becoming enhanced if you just look at explosions. But I did some work looking at the Allied bombing of Europe. And this is a photograph here taken by my aunt, who was an air raid warden in London. Not entirely sure she should have been taking photographs of the air defences, but it is nevertheless a beautiful photograph of a very sinister event. But by looking at the Allied response bombing over Europe, we were actually able to look at the Slough measurements and show that if you took the times of those bombing raids, the strength of the F region above Slough was weakened, and this is compatible with shock waves traveling through the atmosphere, breaking as turbulence in the F region, heating it up slightly, and that change in temperature enhances the loss rate of ionization there. Now, there's also solar eclipses recorded within the ionospheric data, and initially these eclipses were really hit upon to try and understand what was going on in the ionosphere, because by looking at the decay rate of the ionization during an eclipse gives you some indication of the chemistry that's going on there. And so it's the nearest you get to a controlled experiment, really. You switch the sun off with the moon, and then you look to see how fast the ionosphere decays. However, it didn't. These experiments weren't successful because it wasn't really known at the time but a lot of the ionizing radiation, of course, was coming from the corona, and the solar corona isn't eclipsed during a total solar eclipse. The movie to the top left there is one I took during the annular eclipse over Spain in 2005. But what these scientists had inadvertently recorded was the brightness of the corona. And so you can look to see how the brightness of the corona has varied, and it does vary with these eclipse experiments with the solar cycle. But now we have experiments, we have spacecraft like the Solar Dynamics Observatory. It's making very detailed spectral measurements of the sun. And so this was some results from an eclipse in 2015 that was ultimately about 90 degrees over 90% over Reading and over Chiltern. And you can see here the ionosphere decaying away and recovering, and it's been converted to look at the fraction of ionizing, the fraction of the sun that was eclipsed at any given moment. And you can look, those different colors are different wavelengths, and you can see some wavelengths are very closely following the variations in the ionosphere. So if you had very bright regions, active regions in the sun, those will be eclipsed, and you'd have a sudden drop in the ionization in the atmosphere. So technically, theoretically, you could use these historical observations of eclipses to investigate the structure of the solar corona from way before the space age. And then there's space weather events. There's a picture here of a rather giddy space scientist in Oxfordshire in May last year, when the most spectacular auroral displays came as far south as the UK. And the top left panel there is showing you these coronal mass ejections launched from the sun, which were observed by the SOHO spacecraft, which sits between the Earth and the sun. And so you can see, particularly at this moment, all the energetic particles coming past the spacecraft and forming all that snow. When that arrives at Earth, it falls into the atmosphere, causes the air to glow. But you can see with the Chiltern ionograms on the right here, there's a movie at the top there going through the sequence. But when the aurora hits, you get these very fuzzy and broad signals. And this is auroral precipitation. You don't normally get that in Oxfordshire, so very unusual. So all of this is the space weather events are recorded in the data sequence too. And there is also, we've got a very long-term sequence here, so it's a potential source for looking at changes due to climate change. My supervisor, Henry Rishbeth, back in the late 1990s, posed the question, could you detect a greenhouse effect in the ionosphere? And by doing some using the modeling work of Roble and Dickinson, who had shown that if you doubled the quantities of CO2 in the troposphere in the atmospheric models, it led to a cooling of the upper atmosphere because there was less energy being returned to space. And that cooling of the order of 50 Kelvin should result in a lowering of the ionosphere over about 20 kilometers over a few decades as a result. So researchers have looked for this. This is some results from Martin Jarvis et al. In 1998. And you look at the height of the layer, and indeed, it does appear to be coming down. But if you looked at Slough, as Bremer did in the same year, the ionosphere actually looks like it's going up. And the reason that the results aren't particularly telling a consistent story turns out to be the way that the heights are estimated. You remember that the ionoson doesn't measure the height. It estimates the height from the time it takes for the signal to go up and back, and that is delayed by traveling through the underlying ionization. So there have been some empirical formula derived firstly by Appleton in the 1940s and gradually honed to take into account that underlying ionization by using these tabulated quantities, the peak densities of the layers. And we showed last year that if you take one of the quantities in this empirical formula, which is the ratio of the peak F and E region densities, that the formula fails. So here the bottom plot is comparing the height of the layer estimated using one of these formulae with an absolute measurement of the layer height taken with an incoherent scatter radar, the mu radar in Japan. So if these formulae are failing for frequencies that are lower than, in this case, about 2.6 megahertz, then it really matters what the chemistry of the upper atmosphere is. And so any long-term change in the chemistry will change the intensity of the F region, and so it will bring more times or more data down to points where these empirical formulae are not, have some bias introduced into them. And so this explains why we're not seeing a consistent pattern in the decrease of the ionosphere. But the signal's there. You just need to go back to the original ionograms and record the whole trace, and then you can account much more accurately for the underlying ionization. But extracting information from these ionograms is complicated because they are on pieces of photographic paper that are about 1 meter in length, and they don't have any axes on them. If a student handed in a graph this poorly annotated, he'll get a bad mark. But there is information here which we can try to extract. So on a standard ionogram here, so there's the date written in with a black pen on a grey background. It says the 4th of January 1940. There are times, 10:06 here, 10:03, 10 o'clock. It takes about 6 minutes to take an ionogram. You can see the ground pulse here, shown in purple. We can extract the layers. So there's the E region and the F region and the X echoes here. And there are these height markers, so we'd need to know what resolution those were. So we need a Rosetta Stone, really. How can we work out what these graphs are when there's so seemingly all this sort of odd information on them? The Rosetta Stone was a tablet which had the same inscription written both in hieroglyphics and in Greek, and so we understood Greek. That wasn't a lost language, and so we were able to have some cross calibration. Well, we sort of do have a similar thing. We have the engineers' logbooks for the ionosondes, and they're a sequence of rather eclectic leftover pieces of imaginary stationery office, which have, again, not the neatest records, but there's a lot of information going on here. And so there is additional information here which helps us understand how these experiments were being made. There's also some great historical insight. So this is from the 4th of December 1940. So we're into the beginning of the London Blitz here, and they have done the first 2 sections of the graph, and then at section 4 there's just a note which says copper complains concerning candle power issuing from under door. So the policeman had come round and told them to black out their door better because the light was something that perhaps the enemy aircraft could see. So this ruined this particular measurement. There was no record of FOF2 taken at this time because they'd had to stop what they were doing to answer the door to the policeman. Every so often in these logbooks, they do a calibration measure, table, and you can see that they refer to these coils here, and then there's a receiver setting in degrees, and then frequencies. So this starts to look like there's some information here. And if we zoom in, we can see that there's coil 2, coil 3, coil 4, and the numbers here on the left under the coil number 42 and 173, those turn out to be inductance values in microhenries. So what was going on? Well, if you've got if you want to generate a radio signal, you generate a resonance circuit which has both capacitors and inductors in it. And so here we have an inductance coil sitting on a variable capacitor. You could vary the capacitance by putting this connecting rod into the leaves at a different height. And by doing so, you can change the resonant frequency here, omega 0, which is equal to 1 over the square root of the inductance multiplied by the capacitance. So these coil numbers that were referenced in the tables and on the ionograms were different values of inductance coils. And so by putting each one of those onto the box and then changing the dial on the front through a number of degrees, you could generate different radio frequencies. And I got my daughter to plot some of these out. I don't think it's bad, really. She's put good labels on them, and they're quite clearly annotated. I don't know that many of my students put little creatures in the titles, but I allowed her that bit of artistic extravagance. But this enables you to see how the frequency changes with the degrees set on the set. So now if we have a degree number, we can actually work out what the set was broadcasting if we knew what number coil was put into the top. Now the problem is that the electrical components at the time were sensitive to temperature, and so there is going to be a seasonal bias here. We can't just take the coil number and assume it's a set range. So there's a bit more work to do to extract all these calibration tables and see how the frequency range of each coil varied with temperature. But if we do that, then we can start to understand what those different regions of the graphs are and actually extract the frequencies. I think this page was just showing you really that it's, as with every experiment, things can go wrong. There's a recording here from the 16th of April 1935 saying he'd found the camera switched off. So it hadn't been taking the data they thought it had been. There were a few public exhibitions in which they had posters generated, which they had annotated by hand. And so again, we've got some estimate here of what the frequency ranges of each of the coils were. While things were in a state of flux for the early soundings, they did settle down to a routine set of measurements for later years. Well, there's other information that we can extract from these ionograms, and I think it's a case of one man's noise is another man's signal, because there were lots of radio transmitters going on, and a transmitter transmitting at a set frequency will generate a vertical line of interference on the ionogram. And we've got some insight into what radio frequency we should expect. There's a fantastic resource of digitized copies of The Wireless World. In each of those, they would publish tables of the main transmitting stations, shortwave stations, both locally and internationally. And so we can take these values and we can plot them on a graph, and we can sort of say, okay, well, this is what the interference would look like on a given ionogram if it was going from 0 to 15 megahertz. There was also a very big radio station that was very close to the Ditton Park in Slough, and this was Daventry, and it was an international, well, a wireless hub of the empire, as you can see that this article proclaims. And it just made me smile reading this because it's so wonderfully of its time. And the article starts off, to attain in 6 years fame which is first national, then continental, and finally worldwide, falls to the lot of very few towns possessing only 3,608 inhabitants. This is why the 3,608 inhabitants of Daventry gaze at their mast-bespangled hill with gratitude, not to say veneration. Like St. Paul, they are citizens of no mean city. I think, you know, that there was no NIMBYism then. They were looking at these radio antennas and thinking how marvelous it was. I'm sure not all 3,608 were as enthusiastic. But again, we can take the frequencies we know were being transmitted from Daventry, and we can plot them on a sequence of measurements which matches an ionogram and try and match these things up. And you can see that there are some broad matches to the frequency range. There's a cluster here around 6 megahertz, which you can see both in the actual ionogram and the expected transmissions. But there's clearly a lot more going on. So it'd be interesting to see what all those local frequencies relate to. There's a good match at around 3.7 megahertz there too. Well, there are a lot of these ionograms. This is from a video that was done going through the basement at the Rutherford Appleton laboratory. There are filing cabinets and filing cabinets full of these soundings, and they're being looked after by Matthew Wild at the UK Solar System Data Centre. And I really want to preserve these ionograms. They're a unique resource. It's the earliest and longest sequence of ionospheric records, and they're unique. But it's a challenge. We've got all this information to extract. I do have experience with Chris Lintott up at the University of Oxford of setting up a citizen science project known as Solar Stormwatch. We use that to help people or ask people to identify coronal mass ejections in the heliospheric imager images from stereo. And that has produced some great science. It's the human eye is really good at feature recognition, and so looking for these fluffy clouds in solar wind data, people are very good at. And that information from that catalogue is now being not only used for science, but it's being used to train machine learning algorithms to actually automatically identify these things. So I can see a similar project here to extract information, getting people to identify features. And you can see the bottom left here is a bit of a tortuous video of an interface that I've put together to try and help extract some of this information. But it is quite complicated. Volunteers are fantastically good at taking on quite tedious tasks, and they're also quite. This isn't a nice picture of space. It's a black and white photo of some wiggly lines, but our experience has taught us that people are very keen to do that. So we've digitized about 5 years worth of these ionograms so far, and I'm aiming to put a citizen science project together where we can see how accurately we can reproduce these figures, extract information from them, compare them with the tabulated data. I've also had a student project looking to see if there's any way you can automatically recognize features in ionograms using AI. The jury's out on that as yet, I think. Well, that's all I had to say. It's 100 years since Appleton's first experiment. All his data exists. I want to preserve them, and the sequence continues today at the Rutherford Appleton Laboratory. Thank you very much.